Again, so we will resume our session from the unit step response analysis of the system. So in the unit step response analysis, the function is the system function is the first order system. So G of is the first order system, and we represent this by what is plus B. So this is G of is. The inward function is the unit step function, and you already know that how the unit step function is represented. So this is the magnitude of equal to 1 for the duration of the time. So this is the unit step function, and now we are going to find the system response, which is mean that we are going ys, or you can say y. So we are going to analyze the system data. What is the response if the input is the unit step function, and this is the first order system? So we are going to analyze this one. Since you already know the transfer function of the Laplace transform of the unit step function, and the Laplace transform of the unit step function is what is equal to 1 over s. This is the transfer function, which is gs, and y of s, of course, will be equal to what? Y of s will be equal to 1 over s multiplied by b divided by as plus b. So this is the output function. Let us expand this output function. So we just found out that y of s is equal to 1 over s, and then let's simplify this function g of s, and this will be equal to s plus b divided by. And again, we are going to find the inverse Laplace transform of y of s. In this case, it is difficult to find directly the inverse Laplace transform. So what we have to do, we have to use again the partial fraction. So if you will use the partial fraction, then you will get k1 divided by s plus k2 divided by s plus b by m. If you find the value of k1 and k2, then k1 will be equal to what is equal to 1. Just use the partial fraction expansion, and k2 will be equal to minus 1. So this means that the y of s will be equal to 1 over s minus 1 over s plus b divided by m. And directly we have to find now the inverse Laplace transform. So the inverse Laplace transform will be equal to y of t, which is equal to, this is the unit step function now, 1 minus, and this is the exponential function with the unit step function. So this will be equal to e raised to power minus b divided by a multiplied by t. And you can also say unit step function if you like. So you can also write this one. Now, as earlier stated, that we have pole at 0, s is equal to 0 over here, and then we have the pole at any other points. So we said that the pole at the origin will generate the force response of the final total function, and the force at any other, the pole at any other point will give the transient response of the system. This will give the transient response of the system. So if you draw this one, so you see that the output function over here. So you see that what you get, let me use the new variable. So you have this one. So you have y of t is equal to 1 minus e raised to power minus what is called b by a minus b by a multiplied by t. So you have this function. So you see that the first one, this one, This is the this is equal to 1 is the unit step function, and minus this is the exponential function. The second one is the exponential function, and the magnitude. Let me use some more specifically. This is the exponential function. E raised to power minus p by a multiplied by t, and this is t. And this is also magnitude equal to 1. So you see that if you combine the two functions, so the combined effect will be equal to what? So this minus this, this minus this, the first function minus the second function, so it will be equal to 0. So y of t, now this is y of t, and this is the transfer function. So you will get the exponential function like this. And then you have the steady state response like this. So overall, it will be equal to what? This will be equal to 1, and then it is an exponential riser function. So you see that the polar 0, this one is equal to 0 is giving you the steady state response. So this is the steady state response. So this is equal to 1, so it will not go beyond 1. And the pole at any other point is giving you the transient response. So this is the transient state, and this is the steady state. So this is the forced response, forced, or you can also say the steady state. And this is um, the transient, or you can also say that the natural response of the system. Natural response of the system. Also, you see that you already know about the first order system. So, what is the first order system? So, when you have see that in your basic electrical engineering, or you can say circuit analysis, you have the RC circuit or the RL circuit. So, this is you see that if you have one energy storing element, so this is the first order system. For example, in the RC and the in the RL circuit, so what you have the resistor, sorry, RC, and then you have a capacitor. So say that you have this time, the switch which closes at time t equal to 0. So we consider the initial condition equal to 0. Let me erase this one. So this is the switch which closes at t equal to 0, and then you have the DC voltage source. So this is the voltage source. This is the capacitor. This is R resistor. So once you find the equation for the voltage across the capacitor VCT, and you already know that the VCT will be equal to the applied voltage 1 minus e raised to power minus t over R. So we are not going to prove this one because or derive this one because you already know. I expect that you already know. Similarly, you know that if you have the what is called the an RL circuit where you have the inductor, you have the DC voltage source. So this is the input voltage, this is the resistor, this is L. And we said that the initial condition is equal to 0. So you can also say that ILT will be equal to V by R 1 minus e raised to power minus t divided by tau. As tau is equal to L by R is the time constant of the inductive circuit. So this is what ILT. And now from these two expressions, so now here the output over input is equal to what? VL divided by input voltage will be equal to 1 minus e raised to power minus t over. Let's say this is also a time constant. And here you have the output divided by the input is equal to, again, is equal to 1 minus e raised to power minus t over. So you have the response of the system, and the response of the system is giving you the total response of the system, and it has the forced response factor, which is uh, the the one which is this one. Sorry, see, it has two parts. The one is the pole at equal to 0, which give you the forced response. So let use this one, and then we have the second factor, which is giving you the pole at any other point, so it gives you the natural response. So we have the natural response also over here. So we are the system pole at the origin generate the force response, and the system pole at minus b by a generate the natural response. So when t is equal to this a by b, you can say the time constant. So when t is equal to a by b over here, when t is equal to a by b, so what you will get? You will get e raised to power minus 1, e raised to power minus 1, which is equal to 0.37 times. So the natural response will change. You will expect how will decay to 37% of the what is called the initial value. So it will decay to this point, 37% of the final the initial value, this value, 37% of the maximum value. So if this is decaying to 37%, so this means that the total response will changes will be here. The changes if tie is equal to one time constant, so the at one time constant, so you are expecting how much change it? 63% of the changes in one time constant. So when t is equal to a by b, so you will get yt will be equal to 0.36 times of the final value, 0.6. So the value will be equal to 0.36. So this is 63%, which means that the total response reaches 63% of its total change at equal to a by b. So we call a by b as the time constant. So as earlier we said that this is equal to a by b is equal to the time constant tau. It is represented by tau. So this tau is equal to a by b is called the time constant. The system now this is the system response. So note that the smaller the time constant, the faster the time response. Now let us check this one. So this is the uh, response curve. So this is the total response now, which we already used to power minus t over tau. So in this equation, this is t and time t. This is y of t. Now, what is the force response in the final value? The final value is this one is equal to 1. So this will not exceed 1. So let's say this is equal to 1. So now let us find the response when we have the general response. So it will increase like this, exponential function. So this is for the time constant. Now let me say that we are increasing the time constant or reducing the time constant. So you see that when you say that the new time constant dash is equal to 1 over 2 time. So this means you are reducing the time constant. So if you will reduce the time constant, what will happen? So you will get the steady state earlier. See, you will get the steady state earlier. Also, you can expect maximum changes in the one-time constant compared to the uh, term. Similarly, if you say t double dash is equal to 2 times of the time constant, so this means that if you are increasing the time constant, if you will increase the time constant, then what will happen? This will you will slowly get this steady state. So this is steady state. So you see, it will the capacitor will slowly charge, the inductor will slowly get to the steady state position and so on. Moreover, you can also expect that the slope of the response curve decreases from 1 over tau at t equal to 0 to tau equal to infinity. What does it mean by this one? So let us go back to the original function. So this is the steady state position, and this is the response curve. So you see, at one time constant, this is one time constant. Then this is when the value, you can find the values. So how you will find the values? Actually, you have to find the value of yt. So yt for one time constant, so the value will be equal to what? 63% of the final value for one time constant. For two time constant, the value of yt should be equal to, should reach to 85.5%. At three time constant, the value of yt should reach 95%. Similarly, at four time constant, it will reach to 98.2. So at four time constant, this will yt should reach to 98.2% of the final value. So you have to find the time constant. So at one time constant, so you see that at one time constant, let me clearly what is called draw this one. So this is the final value. One time constant. This is 2, 3, and this is 4. And this is 2. Then we have the 3. Then 4. So if you will draw this one like this, and we note these points also. So please check that. Please check this one. Let me use some. So at one time constant, so you see this is the slope. Or the slope is maximum. But as you increase the time constant, so you see the slope is minimum. Here, the slope will become more flattened, and finally, what you will get at four time constant, you will have zero slope. So you see that the slope is also the slope of the response curve decreases if the time is increasing. So initially we have the more slope, which means this means that the system will have maximum changes in the first time constant, and as the time constant is increasing, then the changes will reduce because you will pass the transition state, and then you can enter into the steady state. So this is the steady state point, or the forced response section. So the system passes the transition state, and as it passes the transition state, the slope of this response curve is reducing, or it become equal to 0 at t equal to infinity. So when t equal to t approaches infinity, means for a very sufficient long time, so you will say that the slope will become equal to 0. Now there are some other definitions that we have to look at them also. Um, the first one is the some specific time response specification. So you can say the time response specification of first order system. What are those? These are the settling time. You can say that the what is the settling time. Similarly, what is the delay time? So we see what is the delay time, and similarly, what is the rise time. So let me draw this curve again. So we have this curve. This is the steady state point of the unit step function. So y of t is equal to what? Y of t is equal to 1 minus e raised to power minus t over. And let me also draw the function. This is this one. So we have t, and then we have y of t, and 1 is the final value, or the steady state value. Steady state value. So when we said that earlier, we said that for one time constant there will be the changes. Let me sorry, this one. This one. So you see, for one time constant this much changes, for two time constant this much changes, for three time constant 95% of the value, and then for the four time constant 98.2% of the value. So we say that when the response remains within 2% of the final value, means this one. When the response remains within 2% of the final value, 2% of the final value. So that is called the settling time. So we say that when the response is within this limit, 2% to 5%, even in one of the book in the Ogata, it is said that if it remains from 2% to 5%, that is the allowable tolerance. So sometimes you see that it may not be the steady state, so it can also fluctuate like this one. So you see, if it is higher order system, so it can fluctuate like this. So you may not get the very straight line. So it will. If it fluctuate like this, so there are some ripples. So, but if these ripples remain within 2% of the bounded region, so still it is considered to be a steady state position. So that is why. So if you will, if the response remains within 2% of the final value, so that is called the settling time. So what is settling time? So the settling time, you see, the changes will be from 0 to this point. See, from this point to this point. So this from 0 to this point, this is called TS. So this is the time axis, and this is called the settling time. It's called the settling time. TS, settling time. So generally, if we say that this when this 2% will reach, this 2% will reach when this when we have the time constant is equal to 4. So in the 4 time constant, what is the value of y of t? The value of y of t is equal to 98.2% of the final value. So you see that it is the region where we achieving the 2% of this final value. This region. So the settling time technically will be equal to 4 time constant. So settling time TS will be equal to 4 time constant. Similarly, you see that when the response is increasing, let me use the another marker, black one. So similarly, when the response is increasing from 10%, so this is the 10% region, 10% to 90%. So there will be some point over here when the response will be equal to 90%. So this is 90% of the final value. So when the response is increasing from 10% to 90%, so this time is called the rise time. So this is called the rise time. Rise time. So it's called rise time. So when the response is increasing from 10% to 90% of the final value, this is called the rise time. So what is this rise time? So uh, for this, what we have to do, we have to find the value of t. You see, we have to find the value of t because this data is given. So if this data is given and we are interested in the rise time, which is and the time axis over here, t r rise time. TR is the rise time. So it means that the vertical data will be we are interested in this point on the horizontal axis and this one. So how we will find these axes? We see that these axes can easily be found by using the expression because we have the general expression which is equal to yt is equal to 1 minus e raised to power minus t over. So let's say that yt is equal to 10%, which is equal to 0.1. So this will be equal to 1 minus e raised to power minus t over tau. So now we can easily find the value of the horizontal axis in terms of the tau. So um, if you solve this one, so you will get that t is equal to 0.11 tau. Similarly, we say that 90% of the value, which is equal to 0.9, and 1 minus e raised to power minus t over tau. Now 90% of the final value, since we are using the unit step function, that is why 0.9 multiplied by 1 we are considering. So if this is some another amplitude of the step function, for example 2, then we have to take the 90% of the 2, which means that then we have to consider 0.9 multiplied by 2. If you are considering the step function with what is called, for example, DC signal, and DC signal can be, you see, from ranges from 1 to 12. So if it is suppose if the input function is a step function with magnitude equal to 12, then you have to consider the 0.9 multiplied by 12. Similarly, if it is 6 volt, then 0.9 multiplied by 6. So you have to take consider all this. See, uh, so this means 10% of the final value, and this means 90% of the final value. So I'm erasing this one. And I'm coming back to the original problem. So 90% of the final value, but now here the final value is 1 because we have the unit step function, that is why 0.9 multiplied by 1. So again, you have to find t in the term of the so this will be equal to 2.31. Now if you will find tr, so let me come back to the previous board. So tr is equal to this point. Now we found this point, and we also found this point. So this point minus this point will give you the rise time. So this means the previous point is t2, and this is t1. So t2 minus t1 will give you the rise time. So rise time will be equal to t2 minus t1. So rise time will be equal to sorry, this will be equal to 2.2 ta. So this is the rise time. So this means that the cyclic time is equal to 4 time constants, and the rise time is equal to 2.2 times of the time constant. So we have to find the time constant of the system, and then you can easily find the rise time. Similarly, the third factor is the delay time. So delay time, now the delay time can be easily found because you already know much about now the transient response. So this is equal to e to power minus t over tau, and the so this means this is equal to 1 because of this. And then we have the exponential function, so 1 minus this one, so you are getting the y of t. So you have plot y of t, and this is the time axis. Now the delay time. So delay time is when you are getting 50% of the final value for the first time. So you are increasing from 0 and 50% of the final value, which means in this here we have 1. So 50% of the final value is equal to 0.5. So when y is equal to 0.5, in this case, or you can say 50% of the final value. So this is a more generalized statement. So 50% of the final value then date time. So date time. See this time is called the delay time. So delay time, you see, we can also find the delay time in terms of the time constant. So how you find the delay time? For that we have to test yt is equal to 0.5 and this expression, this one, and then we have e to power minus t over tau. So you will get time is equal to delay time. So you have to find time, and you can find this one something in term of the time constant. So you can easily find this also. You have to find it by yourself. Try this one. Try it, and it will help you to learn also that what is the delay time. So this means that the delay time is equal to this much the time constant. So this was all about the specification of the first time response specification of the first order system, and we can use this for all other signal as well, not only for the unit step function but for the ramp function as well as for the impulse fraction also. Now the second, so what you learn in this topic, so let us generalize this one. Let us elaborate this one, and then we come back. So you see that the unit step function, the unit step function can be used for the transit response analysis as well as the steady state response analysis. So if you are interested to find the stability of the system and you are interested to find the overall stability of the system, then you can use the unit step function, which will give you the transient behavior of the system, and it can also give you the steady state behavior of the system. Now, if you are interested in finding only the steady state error, then we can use the unit ramp function. Unit ramp response analysis. So generally what we have, so we have GS, then we have the input function xt, or you can say xs, and then we have the yt, or you can say y. Yes. What is GS? Since this is a first order system, so GS is equal to B divided by AS plus B. We already know this one. So your denominator has degree of equal to highest degree equal to 1. Now we said that the input function is the ramp function, and the ramp function is represented by this one. So this is called the ramp function RT, and this is XT, and this is the time axis. So R is the representing this slope. So when R is equal to 1, this means that it is the unit ramp function, which is this one. So in our case, R is equal to 1. So mathematically, it can be written as x of t is equal to what? Is equal to t if t is greater than or equal to 0, and otherwise it is equal to 0. So if we have x of t is equal to t, x of t is equal to t, then what is x of s means the Laplace transform of t. We already know that Laplace transform is equal to x of t, which is equal to 1 over s square. So this means that y of s will be equal to 1 over s square multiplied by the transfer function. So this means that y of s will be equal to 1 over s square multiplied by b divided by as plus b. Now let us go to the next slide and then explain this one. So we have y of s is equal to 1 over s square, and then we have simplify this one also, b by a divided by s plus b by a. Now we have a square in the denominator, and we are going to expand this by partial fraction. So remember repeated roots. So we have to use the repeated roots technique of the partial fraction, and then we have to expand this one. So which is equal to C1 divided by um, S square plus C2 divided by S plus, and then we have one real root without repetition. So this is equal to S plus B by A. And now we have to find C1, C2, and K1 by the method that we already described earlier. So if you use that method, then you will get Y of S is equal to 1 over A square. C2 will be equal to minus A by B. In this case, so A by B divided by S, and the K1 will be equal to is also equal to A by B. So this will be equal to A by B divided by S plus B by A. And now we can easily find the inverse Laplace transform of this one. So if you find the inverse Laplace transform of this one, then you will get Y of t, which is equal to uh, which will be equal to t. See, this is equal to t, because the Laplace transform of t is 1 over square, so the inverse Laplace transform is equal to t. This will be equal to the unit step function minus a by b, and then we have the unit step function. You can write, you can also ignore this one, plus u of t. I'm talking about u of t, and then we have the this delay in the frequency or s domain. So it will be represented by the exponential function with the unit step function. So uh, you if you are writing the unit step function, so let me also correct this one. So this will be equal to t u of t, because if you multiply t with the unit step function, so again it will be equal to t plus a by b is the magnitude, and then we have the exponential function e raised to power minus b by a t, and then we have the unit step function. So overall, if you um, let me erase this all this thing and rewrite y of t. So overall, what you will get uh, you will get what you will get y of t is equal to t minus tau plus tau e raised to power minus t over tau, where this tau is actually equal to a by b in the previous equation. So if you will uh, place a by b is equal to tau, so you will get this expression. So let us get this expression, and let us draw this expression. So see that if you will sorry, so what is the input function? The input is the ramp function. So x of t is equal to t is the ramp function. So this is t, and now this is the input function. So this is x of t. This is x of t. And what is y of t? So if you will draw y of t, so it is equal to uh, this one. Similarly, this is for when this is y of t. So you can draw this y of t. Tau is equal to 1. Tau is equal to 1. So if you will draw this tau is equal to 1, so you are getting this expression. Uh, Similarly, if you will draw this for tau is equal to 2, then you are getting this expression. Similarly, if you will draw this for tau is equal to 4, then you are getting this expression. So this is tau is equal to 4. The green one is for tau is equal to 2, and the blue one is for tau is equal to 1, and x of t um, is equal to t, is the input function. Now, what is the error function? So the error signal is actually the difference between the input ramp function and the output ramp function. So see that over here, let me use the blue lines. This is the error function. This is the input error function. So the error function e of t is equal to x of t minus y of t. So this is the error function. You see that as t approaches to infinity, the error function become equal to tau. So if you simplify this one, because x of t is equal to t and y of t is equal to t minus this one. So this one and x of t is equal to what? X of t is equal to t. So t minus this one, and then simplify this one. So you will get what? E of t is equal to. Let me write over here. So this will be equal to tau 1 minus e raised to power minus t over tau. Now it's clear. So if t in this function, you can see in this function, if t approaches to infinity, so e raised to power minus infinity will be equal to 0, and then the error function will become equal to what? E of t as t approaches to infinity will be equal to what? Time constant. So this means that the error function will be equal to time constant. This will be equal to what? This will be equal to tau. When t equal to infinity for a very long time duration. So this will be equal to t tau. So this will give you the what is called the error signal, and the error signal is none, which is equal to the time constant of the system. This means that if you will increase the time constant of the system, so what will happen to the error? The error will also increase. For example, in this case, this is the error. This is the error. In the third case, the error is this one. So you see that the error is increasing as the time constant is increasing. So the blue one is when the time constant is equal to 1. The green one is when the time constant is equal to 2. And the yellow one, the response is when time constant is equal to 4. So you see that when the time response is equal to 4, the error is high, is 4. And when the time constant is equal to 1, the error is small. So such kind of the signal is used to find the steady state error in the system. So as the time constant increases, steady state error also increases. Moreover, the smaller the time constant, the smaller the steady state error due to the input ramp function, which is shown as the red line over here. In conclusion, we can use the unit step function for the transient response analysis as well as the steady state response analysis, and we can use the ramp function for the steady state error, or you can say steady state response analysis. If you are if you are interested in finding the error, what is called the steady state error, then you can use the ramp function. If you are interested to find only what is called the transient response of the system, initial response of the system, then we can use the unit uh, impulse function. So let us use the unit impulse function. Unit impulse response analysis. So again, we have what? We have GS, which is equal to what? Which is equal to B divided by as plus b, and then we have the input function which is x of t, and then we have the output function y of t, and since we can also say y of s, and here we can say x of x. So in the unit impulse response function, the input is impulse function with the magnitude equal to 1. So how it is represented? It is represented like this. Uh, so this is x of t, which is equal to delta of t. Delta means that it is equal to 1 at t equal to 0, and elsewhere it is equal to 0. So you say that delta of t will be equal to what? This is equal to 1 at t equal to 0, and it is equal to 0 otherwise at every other point is equal to 0. And what is the x of s of the delta function Laplace transform of the delta function? This will be equal to 1. So this means that the 1 multiplied by the system response function will be equal to y of s, and this will be equal to g of s, because the input is equal to 1. So now let us use the another board, and let me use this one. Now we have what we have. Sorry, this one y of s, which is equal to what? B by a after simplification. So we can write s plus b by a. And if you find the inverse Laplace transform of this one, so it is straightforward, is an exponential function. So you can write this one. So y of t will be equal to b by a e raised to power minus b by a multiplied by. So let's say that b by a, you can say that a by b is equal to tau. So let's say that a by b is equal to tau. So then you can say that y of t will be equal to 1 over tau e raised to power minus t over tau. So also you say that here we have here, you see, in this function. So you have no pulse at 0, so you have no force response. So you have only the transient response. So because we said that the pole at any other point except 0 will give you the transient response. So and the pole at is equal to 0 will give you the force response. But in this function, the output function, you do not have the pole at is equal to 0. So this means that there will be no response function, and it is clear from the time response analysis also. So again, if you will plot the input function, so this is the input function, so which is equal to delta t x of t. So we say that x of t is equal to delta t, which is equal to 1, uh, magnitude equal to 1. And if you plot y of t, so this is y of t. Remember that we consider tau is equal to what is equal to 1. So if you consider tau, you change the tau, then the magnitude will also change. So you see that very soon it will, you see, it will decay to 0, and you are getting only the transient response of the system. So you are getting only the transient response of the system. So also at t equal to infinity, or t as t approaches to infinity, so this will become the response will become equal to 0 over here. So y of t will become equal to 0, as t goes to infinity. So it is clear that the natural response is initially high. However, the system response reduces to 0 at equal to infinity. So if you, I will conclude over here that if you are interested to find both the initial response as well as the final response, or you can say that if you are interested in finding the transient response as well as steady state response, then you can use the unit step function or the step function. with any magnitude. And if you are interested to find the steady state error, then you have to use the ramp function. And finally, if you are going to analyze the system and you are going to find only the transient response, then you have to use the delta function. Thank you very much for your attention. See you next time. In next lecture, we will discuss the higher order system. So for that time, thank you very much. Take care, stay safe, and do not move outside from your home. Allah Hafiz.